Hi everyone, and welcome back to day 2 of the Science of Cannabis Testing 2022. I'm Roxanne Newman, Senior Conference Producer for Analytical Cannabis, and I'm here to moderate today's talks alongside my colleague Jack Rudd, Caroline Clark, and Athena Hansen-Ahern. Our first talk of the day is Moisture Analysis in Cannabis, How the Standard Method Leads to Inflated Potencies. I'm really pleased to welcome Jini Curry joining us today as your presenter. Jini began working with modern Canna in 2016 and moved into the laboratory director position in January 2018. In 2022, she earned a master's degree in medical cannabis science and therapeutics from the University of Maryland, Baltimore. Jini's current focus at modern Canna is developing standardized methods for analyzing cannabis to ensure harmful toxins are not present. These toxins include, but are not limited to, heavy metals, microbials, mycotoxins, agricultural agents, and residual solvents. Following today's presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. You can also use this feature to chat with fellow attendees, so please do introduce yourself. Lastly, if you experience any technical issues during the presentation, please request help using the technical help icon in the left-hand menu. Now, without further ado, I will hand over to Jini to begin her presentation.
Thank you, Roxanne. As I'm sure many of you know, inflated potency results and lab shopping is a very hot topic in the industry right now. There is new information released daily regarding laboratories who are doing things incorrectly and finding out ways to give growers higher and higher THC numbers for their cannabis flower. While there are laboratories who are bad actors and are purposely skewing results through various processes, there are some labs who are attempting to do things correctly, but are still obtaining higher numbers as a direct result of moisture corrections. So today, I would like to talk to everyone about moisture analysis in cannabis and how the standard methodology leads to inflated potencies. You are probably thinking, so what if a laboratory moisture corrects? It doesn't affect the results that much. However, you'd be surprised by how much the numbers can change depending on how a laboratory is factoring a dry weight correction into their results. Ultimately, as the moisture value increases, so does the correction factor that is applied to the results, which in turn causes a higher potency. When you think about wet weight versus dry weight, you must consider what water content does to results. For example, if you have 10% moisture, then the result is being diluted by 10% due to that water content. So when the water is removed, either through pre-drying the flower or applying a moisture correction, the results will increase by 10%. This is extremely imperative to take into consideration when looking at the concentration of contaminants. However, it isn't as important for potency or terpene analyses. Knowing the true concentration of the contaminants without water content may be the difference between a product passing or failing a lab test that will decide if the product can go to market. This is a whole different conversation though, and I would love to discuss it in detail later. However, today we're going to focus on how moisture content affects the potency results. Before we get into the various nuances of dry weight corrections, let's discuss the standard method for moisture in cannabis. Currently, most laboratories and even some growers use a loss on drying method to determine the water content in cannabis flower. This is done using either a moisture balance, like the one pictured here, or a basic laboratory oven that can heat the samples up. Ultimately, a portion of the sample is weighed and then placed into either an oven or moisture balance that will begin heating the sample. Once the sample has been heated for the designated amount of time, the sample is weighed a second time, and the total weight loss will determine what the water content in the sample is. Since the goal is to remove the water and water boils at 100 degrees Celsius, the sample must be heated to that temperature in order to remove the water that is present. Most methods suggest heating the sample up to 103 to 105 degrees Celsius. If a laboratory is using an oven, the time the sample will remain is determined by the total weight that is used, and laboratories should determine this time as a part of their method validation. With a moisture balance, the sample is heated in a very tiny oven, and the balance will record the weight change over time. Once the weight stabilizes and is not changing anymore, the sample is considered to be dry, and the final weight of the sample is recorded. For cultivators, this type of quick and dirty analysis is great because it gives an idea of how wet their flower is and how much longer it needs to cure and dry before moving to the next step of their processes. However, for laboratories, this is not the most accurate result and does not provide a true representation of how wet the flower actually is. Before we get into why loss on drying methodologies are not a true representation of moisture in cannabis flower, I want to review how moisture calculations work. As I mentioned on the previous slide, an initial and final weight are measured, and the difference between those determines the moisture content. To perform this calculation, the final weight is subtracted from the initial weight, and that value is divided by the initial weight before being multiplied by 100 to get the results into a percent value. I've included an example below. As you can see, the final weight of 1.5376 grams is subtracted from the initial weight of 1.7685 grams, which gives a result of 0.2309 grams. That value is then divided by that initial weight of 1.7685 grams, which is 0.131. To convert this result to percent, it is multiplied by 100, and you get a moisture content of 13.1%. Now let's take a closer look to see how this impacts potency when a laboratory is dry weight correcting. In this instance, the THCA concentration of the wet flower is 24.2%, and the total THC is 22.5%. When dry weight correcting these results, given a moisture content of 13.1%, like our example on the previous slide, you now have a THCA value of 27.3%, and a total THC value of 25.4%. That means the results have been increased by 3.1 percentage points for THCA and 2.9 percentage points for total THC. While this, may not seem like a big difference, the average consumer is going to see that result of 25.4 and think the potency is better and want to purchase that product over the one that is reported without a dry weight correction. Additionally, producers are going to see that result and may decide that the 25.4% THC bud is top tier, while the one coming in at a total THC of 22.5 is mid-tier bud. That may then in turn result in the 25.4% product being sold for $45.08, while the 22.5% product is sold for $30.08. If the flower truly has a moisture of 13.1%, then this would not be false advertisement and the bud would be truly that potent. However, this is where the problems arise. Most people believe that cannabis flower has a moisture of 11 to 15%. However, this is not actually the case. Throughout this presentation, I will provide evidence to support this claim and propose an alternative method for moisture that will allow laboratories to accurately apply dry weight corrections to potency results. To further discuss the concept of moisture corrections and how they impact results, I want to provide a little bit more clarification regarding why dry weight corrections are used and how they work. As previously mentioned, the water content in a sample will dilute out the true concentration of analytes that are present. Dry weight corrections are regularly used in the environmental industry, for example, especially in relation to soil, which may have dangerous contaminants present. During the rainy season, the soil may have more water present due to frequent rainfalls. And if a laboratory tests that sample during this time period, the increased water content will dilute out the contaminants that are present and make it appear as though the soil does not have as much contamination as it truly does. However, if it's not raining regularly and the water evaporates, this decreases the moisture content, thus concentrating the contaminants that are present. In order to correct for this and keep results consistent and accurate, a correction factor is applied to the results that will measure the concentration of analytes when there's no water present. In order to take a result from its wet weight value to a dry weight result, the original value obtained is multiplied by the correction factor. Conversely, if you're going from a dry weight to a wet weight, the results are divided by that same correction factor. Therefore, wet weight to dry weight corrections will increase the final result, while dry weight to wet weight calculations will decrease the final result. This slide provides the same example that was provided earlier. However, I now want to look at the correction factor and how it is actually applied. Previously, we determined how to calculate moisture content based on the initial and final weights of the sample before and after drying. The principle of those calculations will always apply no matter what moisture methodology you're using or how you're removing the water from the sample. As you can see here, we have a THCA value of 24.2% prior to a dry weight correction. We know that the moisture in the sample is 13.1%, which now means that we need to be able to apply the correction in order to obtain the dry weight result. The correction factor that is used to dry weight correct is 100 plus the percent moisture in the sample divided by 100. So in this instance, it would be 100 plus 13.1 divided by 100, which gives a correction factor of 1.131. Therefore, when you take the THCA value of 24.2 and multiply it by 1.131, you obtain the new dry weight corrected result, which is 27.3. The same goes for the total THC value. That wet weight result of 22.5 is multiplied by 1.13 to dry weight correct those results, thus obtaining a total THC of 25.4. In this example, I have only focused on the THCA and the total THC corrections. However, when using dry weight and converting, it must be applied to all analytes throughout the process. Conversely, if you would like to take that dry weight corrected result and determine what the wet weight value is, you need to divide by the 1.131. It is a rather common practice in the industry to provide wet and dry weight results, and that is a lot of times because it will make the flower appear more potent. So if a laboratory certificate of analysis displays both values, you should be able to convert between the two results using this moisture correction factor. Labs are normally required to report that percent moisture, so this is something people can do on their own to make sure the potencies being reported are accurate. Additionally, most modern day laboratory information management systems or LIMS systems will apply dry weight corrections automatically if you tell the software it's necessary. Therefore, laboratories should be able to avoid any transcription errors that may lead to a false result being reported if they're utilizing this type of system. So what's the issue? At this point, you're probably wondering, what is the problem and why are so many people making such a big deal about potency inflation and moisture corrections? On the previous slide, I briefly mentioned that cannabis is often thought to contain a moisture of 11 to 15%. I then made the rather bold claim that this is not true. So I will spend the rest of this presentation focusing on how to obtain a more accurate moisture and how laboratories can avoid erroneously inflating potencies through false moisture corrections. So why does cannabis not contain 11 to 15% moisture? Simply put, the current moisture methodologies cause more than just the water to go up in smoke. By using a moisture balance or oven to perform loss on drying calculations, other compounds that make up a large portion of the cannabis flower are lost in addition to the water content. Most moisture balances and oven drying methods require the sample to be heated to 103 to 105 degrees Celsius. When the sample is heated up to this temperature, cannabinoids that are present are decarboxylated and the terpenes are volatilized. Since these compounds make up a large portion of the cannabis flower, additional weight loss that is not water is being factored into the percentage of water present in the sample. During decarboxylation, 13% of the total amount of the acidified compounds are lost. This means if a flower contains 20% THCA, 2.46% of the total THC will be lost during the decarboxylation process. Similarly, most, if not all terpenes in cannabis will be volatilized at a temperature above 100 degrees Celsius. So if a sample contains 2% terpenes, there's another 2% that's removed during the drying process. We will cover these calculations more in future slides. However, at this point, I just want to get everyone's attention regarding what portion of the weight loss is truly moisture and what portion is the cannabinoids and terpenes that are being lost. Keeping this in mind, you're probably wondering what can be done to prevent this. How can moisture be removed without decarboxylating cannabinoids and causing terpenes to be volatilized? The answer to this question, it can be puzzling. The best way to remove water is to boil it off. However, if you boil off the water, you also compromise the sample and cause chemical changes that will drastically impact the moisture results. Therefore, in order to provide a more accurate moisture result, which will in turn provide a more accurate potency and terpene result, the conversion of cannabinoids and loss of terpenes must be limited during the drying process. Basically, the methodology that is used needs to be able to remove the water from the sample without the use of heat. And the best way to do this is through vacuum desiccation. When using vacuum desiccation, the water that's present in a sample is being removed at room temperature with the use of a desiccant and a vacuum pump. This allows the water in the sample to be removed while maintaining the chemical composition of the product. Primarily, this method will avoid compromising cannabinoids and terpenes that are present. While this method may seem like a foreign concept in the cannabis industry, it has been used for decades by other industries. It is primarily used to determine moisture content in samples that are unable to be placed in an oven. There may be several reasons why samples cannot be heated. However, fertilizer is one of the most common sample types that this process is used for. This type of material is made up of compounds that cannot be exposed to high levels of heat without creating dangerous situations or compromising the integrity of the sample. So laboratories who work in the environmental industry are left with the conundrum of, how do I get an accurate moisture number in my fertilizer without causing problems? I do want to mention that prior to entering the cannabis industry, our laboratory was part of the environmental industry. So we spent many days working with organic materials, testing for pesticides, metals, solvents, and other contaminants that are also measured in cannabis. In doing this, we were able to work with complex matrices that needed extra attention and more method development than standard water or soil samples. And fertilizer was one of these matrices. For fertilizer, there's very specific concentration windows that the compounds present in the sample must fall within. However, the moisture in the sample needs to be factored into those results. Therefore, in order to obtain accurate results for the compounds of interest, the laboratory had to find a way to measure the moisture present in the sample so that proper dry weight corrections could be applied to the results. Knowing what we do about semi-volatile and volatile nature of the compounds that are present in cannabis, we knew that the methodology we had previously used to test fertilizer would be the best starting point for obtaining an accurate moisture in cannabis flower. This is a method we began using in our laboratory over 4 years ago, and we believe that today's presentation will show that though this method may not be perfect, it is a much more accurate measurement for moisture, especially in cannabis flower. I previously explained the process behind running a loss on drying method to determine the moisture in cannabis. Now, I would like to review the method we use internally. Like the loss on drying method, the sample is weighed prior to being placed in the desiccator to determine the initial weight. Since the desiccator is able to hold several samples at once, the entire analytical batch is weighed individually into aluminum weigh dishes that have been weighed prior to adding sample. This allows us to determine how much of the weight is sample and how much of the weight is the container. Once the samples have been weighed, they are placed in the desiccator and the vacuum pump is switched on. This creates a negative pressure environment for the samples and seals the desiccator. The samples are left for 3.5 hours under vacuum at room temperature. After the 3.5 hours have passed, the vacuum pump is switched off and the pressure in the desiccator is carefully released. The samples are removed from the desiccator and immediately weighed to determine the final weight. It's important to note here that when weighing samples post-desiccation, it must be done immediately because if not, states that have really high humidity are going to start absorbing water again and the results will be skewed. And this also applies if a lab is using an oven instead of a moisture balance for loss on drying methodology. Finally, much like the other methodologies, the weight loss that occurs during the drying process is used to calculate the moisture content in the sample. Since the samples are weighed into an aluminum dish and we want to prevent transcription errors from occurring, our formula for the percent moisture calculations are slightly different. We record the initial container weight with no sample present, then add wet sample and record the weight again. Once the analysis time is complete and we are determining our final weight, we record the weight of the dry sample plus the weight of the container. These numbers are then input into a spreadsheet that will automatically perform the calculations included on this slide. For example, the weight of the sample and container is 1.936 grams, and the container weighs 1.3675 grams by itself. When we subtract the weight of the container from the weight of the sample and the container, we obtain an initial weight of 0.5685 grams. Once the sample has been dried, the weight of the sample plus the container came out to be 1.9063. Therefore, if we subtract the weight of the container from the weight of the container plus the dry sample, we obtain a final weight of 0.5388. From this point, the calculations are the same as the ones presented previously. We take that final weight of 0.5388 and subtract it from the initial weight of 0.5685 and divide that value by the initial weight of 0.5685 and multiply it by 100 to obtain a moisture of 5.22%. Some of you may have noticed that we're using much smaller sample volumes than the calculations presented on an earlier slide. And the reason for that is during our method validation process and method development, we determine the ideal sample weight we're looking for is about 0.4 grams to 0.6 grams of wet material. This will ensure that a 3.5-hour drying period is enough time to fully remove the moisture from the sample and ensure that the sample is taken to complete dryness. To establish this ideal weight, the laboratory ran a series of tests where the sample was put under vacuum for specific time periods. Then we stopped it, the weights were recorded at various intervals, and then we determined the point of dryness when the weight no longer changed after vacuum desiccation. Now that I've presented information regarding both loss on drying methodology and vacuum desiccation methodology, we can further discuss the experimental design of our method validation and the evidence that supports our suggestion that vacuum desiccation is a more accurate way to obtain moisture in cannabis flower. For this validation experiment, we selected a total of 17 samples. These were various sample types from various clients. We included pre-rolls, whole flower, small buds, and ground flower in the study. By doing this, we can ensure that the methodology works regardless of the flower matrix being used. After selecting our samples, we processed them in 3 different ways. The first way of processing the samples included performing no moisture analysis. We strictly ran the samples wet for both potency and terpenes. And this is the way that laboratories should be processing samples because any type of pre-drying could impact the integrity of a sample. So if dry weight corrections are applied, they should be applied after the fact, and the samples should not be dried. Next, we took additional aliquots of the same 17 samples and ran them for moisture via vacuum desiccation. All samples were processed in duplicate for moisture analysis, and this allowed us to gauge the reproducibility of the methodology and also ensured we had enough dry material left to use for potency and terpene analyses post-vacuum desiccation. Similarly, we took another additional 17 aliquots of the same samples and ran them for moisture via loss on drying. Our laboratory does not have a moisture analyzer, so the samples were prepped in an old school oven drying method, and we were able to calculate that loss. We again determined the amount of time that the samples should stay in the oven, and we found that using the same exact parameters we used for vacuum desiccation of 0.4 to 0.6 grams of starting material and 3.5 hours of drying was a really good time point for this experiment. Once the sample was dried, similar to what we did with vacuum desiccation, we then took that sample that was remaining and ran potency and terpene on it post loss on drying. This graph includes the moisture values that were obtained for both methodologies. As you can see, the vacuum desiccation method presented in green on the graph obtained much lower potency or much lower moisture values when compared to the loss on drying methodology. The average moisture via vacuum desiccation is about 3.65%, while the average for loss on drying was 10.99%. Additionally, the graph provides a clear trend that indicates the higher the moisture via loss on drying leads to a higher moisture via vacuum desiccation. While the samples do not line up perfectly, you can see a clear up and down trend for the samples when they're processed for moisture. The average difference that we saw between the two methods was 7.34% moisture. Additionally, both methods obtained extremely reproducible results, and the relative percent difference between each sample for both methods was less than 1%. This indicates that both methodologies are reproducible and that the numbers obtained can be recreated. So the biggest question this data poses is, what result is more correct and which result is a true reflection of the water content in cannabis flower? So in order to better explain the reasoning behind the use of vacuum desiccation for this type of product, the potency and terpene data will be used to show that the loss on drying methods lose more than just water from the sample. And as a result, the percent moisture values that are traditionally reported in the industry are skewed high. I would like to mention that you will probably notice that I have used a red box to outline sample 15. Throughout the rest of the presentation, we will be using this sample as an example. And so to start, we want to mention that via vacuum desiccation, the moisture obtained was 3.47%, and via loss on drying, the moisture was 10.61%, which is a difference of 7.14% between the two. So once the moisture analysis was completed, everything was calculated, we were ready to run terpenes and potency on both the vacuum desiccation sample and the loss on drying sample. Additionally, we also ran potency and terpenes on the wet samples. So when processing samples for potency, the following information was revealed. As you can see, the wet samples and vacuum desiccation samples have low levels of THC compared to THCA. Our example shows that the wet sample contained delta 9 THC at a value of 1.27%, and the vacuum desiccation sample contained a delta 9 THC at 1.3%. However, if you look at the loss on drying, you'll see that the delta 9 value is 21.8%. This indicates that that sample underwent decarboxylation during the drying process. So this can also be confirmed by examining the concentration of THCA, the carboxylated version of delta 9 THC. And for this analyte, the wet sample and the vacuum desiccation sample had very similar values of 24.2 and 23.8, while the loss on drying sample only contained 0.111% THCA. It's important to note that when cannabinoids are decarboxylated, they do lose that 13% of their weight. This is something I mentioned earlier as well. And so this is occurring because the carboxyl group that's attached to the compound is removed. This slide focuses, strictly on the conversion of THCA to delta 9. However, other acidified compounds such as CBDA and CBGA, which are prominent in some flower samples, will also undergo a similar conversion and weight loss when heated. Since we have looked at the numbers, I think it's also important to look at the data for this. So the spectra presented is a zoomed in version of the chromatogram that shows the elution of both delta 9 THC and THCA. The pink data is going to represent the wet sample, the blue represents the vacuum desiccation sample, and the black represents the loss on drying sample. As you can see, the flower that was heated to remove the water had complete decarboxylation of THCA to delta 9 THC, while the wet sample and the vacuum desiccation sample look almost identical. And any of the little differences you see in that are probably small deviations in sample prep, such as how much was weighed. So 0.2035 versus 0.2001. And so what you can see here is this is confirming that while the loss on drying method does remove water, it also has additional loss that's not associated with water content. When determining the loss that occurs as a result of decarboxylation, the THCA value must be multiplied by 0.877, and that value needs to be subtracted from the raw value for THCA to determine the amount of loss that has occurred. This next slide is going to show some additional spectra for the same sample, and the spectra on the bottom here is a 10 ppm cannabinoid standard that contains the following analytes in order from left to right. It's going to have CBDV, CBDA, CBGA, CBG, CBD, THCV, CBN, delta 9 THC, delta 8 THC, CBC, and THCA. It is clear that the decarboxylation of cannabinoids took place in the sample that was heated, while the sample kept at room temperature under vacuum desiccation did not experience this phenomenon. The next subject I would like to discuss is going to be the loss of terpenes that occurs with both loss on drying and vacuum desiccation methods. While today's presentation is primarily focused on potency and the impact of dry weight corrections and inaccurate moisture calculations, terpenes must also be considered when explaining why the current methodology is skewing the results high. In these tables, you can see the total terpene percentages for all three sample preps. So the wet sample clearly contains the highest terpene values, followed by the vacuum desiccation sample. The loss on drying samples, they contain no terpenes across the board. They were all gone, every single one. And this shows that, so basically, while vacuum desiccation does a better job of preserving terpenes because it's at room temperature, it doesn't 100% preserve terpenes. And so what we pretty much saw was the average loss of about 40% through vacuum desiccation. However, when you're comparing that to a loss on drying percentage of 100%, the 40% is a much better value. And so quick thing to point out is the sample we'll be focusing on for our example calculations is sample 15, which had a total terpene percentage of 1.25. So this slide is going to show the spectra for sample 15. And the pink spectra is going to be for the wet sample, the blue will be for vacuum desiccation, and the green is for the sample that was prepped via loss on drying. Again, like potency, this shows that the loss on drying method compromised the sample much more than the vacuum desiccation method did. Previously, I mentioned that terpenes are volatile and they also have semi-volatile properties, meaning they go up and out once they're heated. And it's important to know that we see more degradation on lighter terpenes than we do on the heavier terpenes. And this can be explained by the molecular weight and the chemical makeup of those compounds. Monoterpenes such as limonene are much easier to remove and can be lost by simply opening a container of cannabis flower and leaving it on a bench top for a few hours. Diterpenes, however, are much heavier, more stable, and therefore removing them during the vacuum desiccation process is difficult without the addition of heat. And so you can see that those are much more preserved, and you can see those on the right side of the spectra versus the lighter terpenes, which are going to be on the left side of that spectrum. So looking at this slide, we have kind of confirmed yet again that the weight loss measured when determining moisture content in cannabis by a loss on drying method results in additional weight being included that's not actually water content. And, terpene concentrations in cannabis flower will often range from 0.25% to, 4%, depending on the sample. Therefore, if a sample is on the higher side of that and is, say, 3% and is heated to 103 degrees Celsius to remove the water, there is now an additional 3% moisture that does not actually exist. Now that we have discussed the results and looked at how the plant is compromised during the drying process, we can further discuss the impact that the dry weight corrections have on the potency results for a sample. In this example, I've included the potency for the sample that is measured at wet weight and then again moisture corrected by both vacuum desiccation and loss on drying. Previously, we discussed that the correction factors to go from wet weight to dry weight can be determined by adding the moisture content to 100 and dividing by 100. So in this example, the moisture percentage for vacuum desiccation is 3.47%. So that correction factor is going to be 1.0347. And in multiplying that out, you're going to see that THCA value go from 24.2% to 25%, and the total THC value is going to go from 22.5% to 23.3%. And then the loss on drying sample, we have a moisture of 10.61%. So in this instance, the correction factor for that result will be 1.1061. And this will increase the THCA result from 24.2% to 26.7% and increase the total THC value from 22.5% to 24.9%. As such, the correction factor that is applied based on the lost on drying method increases the result significantly compared to the increase seen when factoring in dry weight correction that is obtained using a vacuum desiccation methodology. We are looking at, potency increases of 0.8 for THCA using vacuum desiccation versus 2.5% THCA using a loss on drying method. To better visualize why the loss on drying is inaccurate and why the vacuum desiccation method for moisture is much more realistic for cannabis flower, we need to measure the total weight loss that occurs when the cannabinoids are converted. So we know that the loss that occurs as a result of decarboxylation is about 13%. Therefore, when you're doing calculations to determine the total cannabinoid loss as a result of decarboxylation, we're multiplying the concentration of the acidified compound by 0.877 to obtain the final value for the decarboxylated compound. Once that number is obtained, it can be subtracted from the concentration of the acidified compound to determine the overall loss. With this information, we know that the overall loss for THCA is 2.977, and the overall loss for CBDA is going to be 0.00578. And finally, the loss of CBGA is going to be 0.15744%. So when we add these all together, the sample experienced a total cannabinoid loss / conversion of 3.14%. And that's if a sample is completely decarboxylated, which the data showed that did happen. So we need to now take that into account when looking at a moisture via a loss on drying method. So with that information, we can, and the total percentages of terpenes, which is going to be 1.256, we can take those losses and combine them to determine how much loss occurred just as a result of potency and terpenes. And so in this instance, we're looking at 4.396%. And then when this is added to that moisture of 3.47%, we now get a value of 7.866%. And this should be fairly close to the moisture value that was obtained via loss on drying, as it takes the loss of terpenes and the conversion of cannabinoids into consideration when determining the final moisture percentage. So as you can see here, the moisture obtained via loss on drying for the sample was 10.6, and the combined loss of cannabinoids and terpenes plus the moisture vacuum desiccation method was a total loss of 7.9%. So this means the remaining difference between these two methods is about 2.7%. So what's missing? Why is there an additional 2.7% that cannot be accounted for between the moisture obtained by vacuum desiccation versus the moisture obtained via loss on drying? And the answer to that question is simple. There are several other compounds present that are not being considered when calculating total loss. The methodology we use internally for potency and terpenes do not include all of the potential compounds that exist. Additionally, the laboratory does not run the samples for flavonoids or other fats and oils that have semi-volatile properties. And we know that those compounds also make up a decent percentage of the cannabis bud and must be considered when trying to measure the true water content in cannabis. Ultimately, the experiment performed has proven that while the vacuum desiccation method is not perfect and does lead to some terpene loss, the values are much more accurate than the ones obtained when heating the sample to remove the water. The loss of cannabinoids and terpenes alone can make up several percentage points, and that value impacts the total loss in moisture content that's present in the sample. If that loss is not considered when looking at the total moisture, the water content being measured via loss on drying is being overestimated substantially. As a result, any dry weight corrections that are applied to terpene and cannabinoid concentrations will result in inflated potencies and inflated terpene results due to them not being truly representative of what is present in the sample. So to provide consumers with the most accurate potency values, the industry should move away from measuring moisture content via loss on drying and move towards analyzing the samples via vacuum desiccation. This methodology does a much better job of preserving the sample and does not alter the chemical makeup in a way that will drastically impact the results that are obtained. The evidence presented within this presentation has supported this suggestion and shown that the loss on drying methodology is what is leading to erroneously inflated potency numbers. So when keeping this in mind, it is important to note that moisture corrections can be applied to cannabis samples appropriately if a laboratory obtains the moisture content and performs the calculations correctly. The environmental industry has been doing moisture corrections for decades, and these calculations are required for solid samples when a laboratory is determining the final concentrations of the compounds being analyzed. Ultimately, one of the biggest problems with moisture corrections in the cannabis industry is that laboratories are not properly analyzing for moisture present in cannabis flower. And that's simply due to the complex nature of cannabis and the volatile and semi-volatile properties of the compounds that are present. So as a result, moisture must be analyzed via a method that does not apply heat. Ultimately, moisture correction of 6% will only increase your results by 1.06%, while if you have 13% moisture, you're increasing those results by a factor of 1.13. And this is the difference between obtaining 20.4% THC wet weight and 21.6% THC or 23.1% THC if you did vacuum desiccation versus loss on drying, respectively. So as such, in this instance, the most accurate and true value is the one with the moisture correction taken into consideration that was obtained via vacuum desiccation. And so that in that instance, that value would be 21.6. However, the problem that we run into here is because the standard methodology that is being used is not well suited for cannabis, and laboratories have found ways to over dry and manipulate the moisture values. Laboratories need to be forced to report on a wet weight basis until more industry standardization can be created. Finally, before wrapping up this presentation, I would like to provide some tips and tricks for spotting potency inflation that is directly related to moisture corrections. So there are several states that will allow laboratories to report potency at both a wet weight and dry weight correction. And if this is the case and you are provided with two potency values, the moisture correction calculations presented within this presentation should allow you to convert the results back and forth between the wet and dry weight values using only that reported moisture value. And if you are not able to do that, that could be an indication that something is being done incorrectly. Additionally, if a laboratory is reporting a potency that has been dry weight corrected and the methodology used to obtain moisture was loss on drying, it's best to just assume that the true potency is lower than what is actually in the sample. So while an increase of 3% THC may not seem like a big deal to some, it is negatively impacting the cannabis market right now, and it's causing consumers to pay more for bud that does not contain the amount of THC that the label claims. And finally, if you have more questions and want to better understand the laboratory's processes, asking for the standard prep weights will help you ensure that dry weight corrections are not being applied in multiple steps of the process. So the dry weight correction should be applied only at the end, and the sample weight, prep weight should not change based on the moisture content in the sample. So samples should be analyzed wet without any drying. And, sample weight should be 0.2035 to 0.2001. There shouldn't be a big variation up and down of what their standard protocol calls for. So in that instance, that's an example of, the protocol calling for a weight of 0.2. Really, in an ideal lab situation, you should be weighing between 0.1950 and 0.2050 for that type of sample. And laboratory information management systems, so the LIMS systems, they're a great tool for laboratories, and they can ensure that laboratory processes are being handled appropriately, that conversions are happening correctly, and that nothing is being skewed due to errors in calculations that are human error. So I hope that you guys all enjoyed today's presentation. This slide provides some of the references that we used for the information presented within, and I hope you enjoyed it.
Thank you very much, Jini. A brilliant talk to kick off the day today. I know we are quite short on time, so we'll move straight onto the Q&A session now and get through as many questions as possible. And please do remember to submit all your questions for Jini into the box to the right of this live stream screen. So let's jump in here with the first question. Is there a formula that can be used to show the correlation between the moisture determined with a moisture balance and the moisture your laboratory is obtaining?
Yes, and so I think that calculation was presented on one of the previous slides where we were taking, the moisture we obtained plus the total amount of terpenes plus the total cannabinoid conversion. And when you add those values together, you're going to get a value that is looking at total loss, similar to what a loss on drying method looks like.
That's great. Thanks, Jini. And the next question, which is probably on a lot of people's minds, if this method is proposed to be better for determining moisture content in cannabis, why is it not being used by a larger number of laboratories?
So this is an interesting question. I think the industry is just so new that it hasn't really been established that this is the better option. Everybody wants to believe that the cannabis is 11 to 15% moisture. And so because of that, no one's ever really challenged that and looked for a better, more accurate method. Moisture balances are great. They're super easy to use. You throw a little bit of sample in it, you're good to go. Whereas performing a vacuum desiccation has a little bit more sample prep involved. And so I think people have kind of avoided it some for that reason. However, looking at vacuum desiccation, cost effectiveness is way more cost effective than a moisture balance. So that is, for us, another thing we recommend to our cultivators is that if they want to do this in-house, this is something that they can do internally rather than using a moisture balance.
That's fantastic. Thank you, Jini. And the next question is in relation to that question, actually. Do you believe that this method will be adapted as the standard for cannabis flower?
I hope so. I hope that, through this presentation and through the study that we did here, we'll be able to get a little bit more exposure for vacuum desiccation methods versus the loss on drying methods, so that we can begin questioning kind of how moistures are being obtained and why moistures are being obtained the way they are. And part of what I'm doing is in hopes is, working with organizations like AOAC in order to try to create these standard methods. So what we're doing internally, we've spent a lot of time working on, and I think that it is truly more accurate than a moisture balance. And so I ultimately hope that it can be adopted as a standard method.
Absolutely. Thank you, Jini. And I think we have time for one more question, one quick more question. So the last question here, you mentioned that laboratories use moisture corrections to inflate potency results. Do you have examples of other ways potency is being inflated?
Yes. So this is a very hot topic in the industry right now. We're seeing more and more lawsuits coming for false label claim and for inflated potencies and laboratories doing things that they shouldn't be doing. And that's where this becomes a little difficult, because laboratories on the front end can find ways to inflate potency that will not make it noticeable to a consumer or a cultivator or a processor who is having those tests done in the laboratory. So people may be not making their standards correctly and making a 90 ppm top of their curve, but calling it 100. Or laboratories may be weighing different amounts than what their protocol calls for. Laboratories may not be diluting to the proper volume. So there's lots of things that can be done. And so ultimately, tighter regulations and people going out and investigating what laboratories are doing and watching them through their entire process, reviewing their SOPs, performing audits. I think that is how we're going to eliminate a lot of this potency inflation, along with the use of, standardized methods. If everyone has to run potency the same way, you're going to have a lot better shot of people obtaining the same value than if everybody can run it a little bit differently.
That's great. Thanks, Jini. A great message to end on there, particularly as you say, this is such a hot topic at the moment with the recent potency inflation that we've been seeing in the industry. So yeah, great note to end on. Unfortunately, that is all the time we do have for today, but any questions that we didn't have time to get to will be sent to Jini and answered offline as soon as possible. And as we wait for our next speaker, please do make use of our networking tools located in the left-hand menu. So that just leaves me to say thanks again to Jini, and we'll be back soon with the next talk. Thank you.